Good morning. Welcome to the second day of the Simon's 10th anniversary workshop. The first talk today is by Irit Dinur. Irit Dinur needs no introduction. We know her through a lot of work on the new proof of a PCP theorem, high dimensional expanders, and lots of other things. Today, Irit will tell us about some of the breakthroughs in locally testable codes. Irit.
Okay, hi. Thanks for the introduction. You can hear me and you can see me? No?
Yes.
Yes.
Okay, all right, thank you. Okay, hi everybody. Thanks so much for the invitation to participate in this wonderful celebration of the Simons Institute 10th anniversary. I'm really sorry to not be there with you in person, and I'm saying that not because it's a nice thing to say. Really, I feel like I'm missing out. Unfortunately, there was also, as you may probably have heard, there was a big conference here celebrating Moni Naol's 60th birthday, which ended, well, it's actually going on still right now. So I had to choose. But anyway, I really, in my heart, I'm also at Berkeley, and the Simons Institute has played such a big role in this research community. It's a bit hard to believe that it's only been 10 years since its inception. It's had a huge impact, I think, on the entire community, but I can say for me personally and the students that I know. And so honored to be part of this celebration. Okay, so I'm going to talk about expanders, expansion, starting with graphs and then moving to codes and PCPs and proofs. So let's begin. Yeah. All right, so expanders. Expanders are such a fundamental thing these days in theoretical computer science, also in other areas in mathematics, group theory, geometry, and so on, that I really don't need to explain or define what they are, but let me do it anyway. So expanders are graphs that contain some interesting contradiction in that every vertex in the graph, you can think of it as a network. So every vertex is like a person on a network, and it's only connected to a very small, like a constant number of other vertices. So the degree is very small, the graph is sparse. And the contradiction is that even though it's very sparse, it's highly, highly connected. And this is an expander graph. Highly connected means that there's no way you can kind of take a bunch of vertices and cut them away from the graph without having to cut many, many, many edges. Okay, so it's robustly, it's not only a connected graph, it's robustly connected. And this is kind of the most straightforward way in which we think about expander graphs. And there have been so many applications of expanders in computer science. By now, I don't need to enumerate them. Let me just give one example that will be important for this talk. And this is the application to error correcting codes. So what are error correcting codes? In the digital age, we have data being stored digitally, transmitted digitally, and noise and errors happen all the time. So bits get flipped for various reasons. And a lot of the data, it's okay if some bits get flipped in a photograph, nothing will get ruined. But in some data, like in finance or if it's a computer program and some bit gets flipped, everything will be ruined and you won't be able to understand what's going on, or worse, you might do something completely wrong. So we must protect our bits and be able to recover from any error that happens. And this is why we don't just transmit the bits as they are, we actually encode them. And the hope is that we don't need to use too much overhead and yet be able to recover from any errors. You know, every person encodes his transmissions. When you speak to someone and there's loud noise, you might say the same thing twice or three times until you're sure the other person heard. But that's a bit wasteful. If you say something three times, you're only using a third of your channel. And error correcting codes allow you to do it much more efficiently. So what is an error correcting code? It's like a dictionary. It's a bunch of strings, and you have a mapping from a message to a code word. And instead of transmitting the message, you transmit a code word. And the nice thing about the code words is that the guarantee is that every pair of code words is far apart, so many bits are different. And so if you transmitted the code word and a few bits got flipped, the receiver will just search. He got some corrupt code word. He will search in the space of around the corrupt code word until he finds the nearest actual code word, and he knows that this is what you transmitted, assuming not too many errors have happened. Okay. So of course, the way I describe it, the search space can be exponential. That's not a very good thing, but a good code comes also with a good decoding algorithm, so you don't really need to search in an exponential search space. And this is the decoding problem. You're given a received word, you know some errors may have happened. How are you going to clean it and remove all the errors and find the nearest code word? So a beautiful construction in '96 by Sipser and Spielman show how to use expanders to construct error correcting codes that can be decoded in linear time. And in a paper, I think in the same year, Spielman also showed how to construct another code that can actually be also encoded in linear time. And for this, they used expander graphs. Now, the question of error correcting codes suggests some kind of geometric thing, because you're trying to put points in this Hamming space and you want to put them far apart from each other. Nothing in this problem suggests using an expander graph, which we said is like a robust network. But somehow this is useful. And the way it's useful is that their idea was to use the expander to describe the linear constraints of the code. So for example, you would put a constraint, you would put bits on the edges, and you put constraint around every vertex. And the reason, and because the constraints are on an expander, means that you cannot just put a bunch of ones in a small location and everywhere else zero without many constraints being unhappy. Kind of many constraints will see both the ones and the zeros and not be satisfied. So somehow the expansion is pushing the set of ones to expand and expand, and that gives you distance between different code words. Furthermore, the expansion allows you to have a bit flipping algorithm that basically looks at a bit, and if the constraints around it are unhappy, just flips it. And somehow this simple algorithm will converge to the non-corrupt code word if your graph is sufficiently expanding. So somehow expansion plays an important role in this, both in the construction, proving distance, and also in the algorithm. Okay, another application of expanders. Of course, there are many, many applications. I just chose the ones that fit my story. Another application is for PCPs. So before I describe the application, let me tell you a little bit about PCPs. These are probabilistically checkable proofs. So this is really a celebrated theory within theoretical computer science. The famous PCP theorem was proven more than 30 years ago. And what it says is that every NP statement, a statement that you can prove with an NP witness, you can actually prove in a much more robust fashion, in a way that it can be checked, verified, not by reading the entire proof and checking it, but rather by doing some random test. And this random test will only read a constant number of bits in the new robustified PCP proof. So the statement is almost, it's hard to believe, it's almost unbelievable, because proof is such a volatile object. You know, a bug somewhere can really ruin the entire proof. So how can you make it into a robust object? Nevertheless, by now, it's been 30 years, we got used to it. So we know that PCPs exist, and we understand the formalism that allows this to happen. I'm not going to go into all the details, just to say that we really have a very well developed theory around this and many, many applications, both to optimization, to prove hardness of approximation, and even to much more new and modern real-world applications to cryptocurrency and cloud computing, where you have this asymmetry between the cloud that has a lot of computing power and your mobile phone, say, that has a small computing power, and you want to check that your cryptocurrency is being constructed correctly, and you want to do this without spending too much computation power, so you use these kinds of PCPs. Not exactly only that, you need some crypto and so on. And it turns out that, like in the case of error correcting code, expander graphs are useful components in some constructions of probabilistically checkable proofs. And let me tell you a little bit about that in one more slide. But just a minute. How can I pick? Okay. So I think I'm missing a slide. I was supposed to, let me pick forward. Yeah, okay. I meant to go to this slide. Okay, so I want to show you how expanders are useful in constructing a probabilistically checkable proof. So you need to kind of believe me that to prove the PCP theorem, it's enough to prove a certain statement about three coloring. And the statement is that I have a graph. I don't know if it's three colorable or not. And there is I can define something called a gap. So the gap is between, in one case, the graph is completely three colorable. And in the other case, there is some, no matter how you color the vertices, there is some fraction of edges that are going to be poor, they're going to be monochromatic. They are not happy with this coloring. And the PCP theorem is equivalent to being able to take this graph and encoding it into a new graph, so that if before you just knew that in the yes case, the graph is colorable, and in the no case, it's not colorable, after the transformation, there should be a gap. And in the no case, the graph should be not only not colorable, but actually any coloring must violate at least 1% of the edges. If you had that, then a test of the colorability of the graph is just to select a random edge, read the two endpoints, and with probability 1%, you'll catch a lie. So if you repeat this 200 times, you will have very high probability of catching a prover if he's trying to convince you of a false statement. So you only need to read 200 colors and not the entire proof. And the way in this proof we do it is by slow steps of gap amplification. Every time we take the graph that we have and we kind of push the colors through an expander and create a new vertex for every little ball in the old graph. And we use the expansion of this graph to argue that somehow the colorability of the new graph became worse than it was before if it was not colorable. So if there was already any coloring needed to lie and to have some errors, then after this expansion, the number of errors must be spread out even more. So somehow the expansion is allowing us to spread the errors, and this is kind of the gist of the proof of this gap amplification. So this was a paper from, I don't know, more than 15 years ago, and it was very nice and showed that PCPs can be constructed based on expander graphs. Okay, so now I want to kind of step back and talk about expanders a little bit more. So first question we can ask is, do expanders even exist? I guess at this point it's a bit redundant to ask this question. Expanders are everywhere. It is known that a random graph is a good expander. And we also have very good constructions, number theoretic and group theoretic constructions that give best possible expanders if you measure it in terms of eigenvalue gaps. We also have a really, really beautiful construction by Reingold, Vadan, and Wigderson that construct graphs by very elementary methods, a kind of recursive construction called the zigzag construction. But let me talk a little bit more about the LPS construction, because it will help me to get to the high-dimensional expanders. So Lubotsky, Phillips, and Sarnak in 1988 constructed the Ramanujan expanders. And the way they did it is they started from the infinite tree. So here in the picture, we see an infinite three regular tree. So here is a vertex, it has three neighbors, and then each neighbor also has three neighbors, and so on and so on. It goes all the way to infinity. And you can associate vertices of this infinite tree with a certain group, and then use a subgroup to kind of glue together different vertices if they're in the orbit of this subgroup. And this gives you a finite object. And what LPS proved is that this finite object is a very, very good expander. And this has had tremendous success, many applications. And so following this tremendous success, Lubotsky, Samuels, and Vishne, maybe almost 20 years later, thought maybe we should try to continue this line of work in higher dimensions. So just like there is an infinite tree, there are also higher dimensional analogs. This one is called the Brotitz building. This is just like a graph where you have vertices and edges, but instead of only stopping there, you also have higher dimensional faces. In this picture, we also have triangles. So that's like a two-dimensional face because it's like a little plane. Okay, and so what LSV did is that they took this Brotitz building, and the way we should think of this is that you have a triangle. On every edge of the triangle, you glue more and more triangles, and then each triangle on each one of its three edges, you glue even more triangles, and so on and so on. So it's like an infinite tree, but it's like a tree of triangles. Okay, so what they did is just like in the infinite tree, you can use groups that act on this building and use that to make a quotient that is a infinite sequence of finite quotients. And these are quotients of the Brotitz building. You get a finite construction. It's really beautiful. It uses deep mathematics. It is somewhat inaccessible, but slowly and surely we managed to understand more aspects of it, even without needing to understand the entire deep theory. And for example, now we can look not only at random walks moving from vertex to vertex, but also at random walks that move, say, from edge to a triangle, to an edge, to a triangle. So there are many more random walks that we can look at. I'm not going to define what a high-dimensional expander is because there are several definitions and it's a new theory and it's not quite stabilized yet. So I think that instead it's better to just understand what is a high-dimensional graph. It's just a graph that also has triangles. And the property that really captures kind of an interesting phenomenon here is this local to global, looking at little pieces of the complex through this notion of a link. So here is a high-dimensional graph that I drew, a simplicial complex. And you see it has vertices, edges, and triangles. And I want to define what is a link. So a link of a vertex, I just fix one vertex, you see it here. And now its link is like its neighborhood. The vertices of the link are all the vertex neighbors of this guy. And the edges in the link come from the triangle. So if this vertex and this vertex share a triangle with our center, then we put an edge in the link. So in this picture, the link of the pink vertex in the middle is this 5 cycle over here. And it turns out that in high-dimensional expanders, just by understanding things about the links, you can gain a lot of understanding about the global structure of the entire object. Okay, one really, really beautiful theorem is the trickle-down theorem of Ishar-Oppenheim, which is a kind of, in some ways, dates all the way back to Garland from 1973. And this theorem says that if you have a high-dimensional graph and every link is an expander, and you need it in some quantitative way, then the entire graph is an expander. Or more accurately, the entire connected component is an expander, because of course we can take separate copies and the links won't know it. Okay, so high dimensional, so okay, let me stay here for a minute. So this is the kind of, historically, it's like the beginning of how we understand a high dimensional expanders. The whole structure is very hard to grasp, but this idea that the links give you something about the whole object. So let's just look at the links. And for me and other people like me, if you're used to thinking about PCPs and property testing, where you try to understand a global object by looking at local parts of it, high-dimensional expanders seem like a wonderful gift, because they're very different from things we know, and yet they have this property, and you feel like, wow, this must be useful for something. Okay, so one of the first kind of big successes of this theory was an application to fast mixing of random walks. This actually has to do also with the Simon's program, but I'll skip this slide because I don't have enough time. But this is a really beautiful result where they used high-dimensional expansion to analyze some very important random walks on matroid bases. I want to get back to error correcting codes to connect to the stuff I talked about before. So as we already saw, error correcting codes are often based on expansion and expander graphs. And when we started to learn about these high dimensional expanders, it was very natural to wonder if we can use them to create error correcting codes with new properties. And there was a Simon's program in 2017 on pseudo-randomness, and I happened to be there in part of the program. I spent some time with Tali Kaufman and others, and here is a talk that I gave. You can almost ignore the abstract, just the title says high-dimensional expanders and PCPs. Now, it's not that I knew how to construct PCPs with high-dimensional expanders. It's more that I was talking about the analogy between these two objects and how they feel similar, and we should be able to combine these two things. So this was like kind of a dream that hasn't yet materialized, maybe in the future. But while we were around the Simons at that time, we talked. We happened to meet Amnon Tashma, who was on sabbatical at Berkeley back then. And we talked about error correcting codes, which seems like a natural next step. And this ended up being a paper with Tali and Amnon, and also with Prahlad Harsha and my student in Bal Livni Navon. We showed that certain constructions of error correcting codes that were already known, if you do them not on expanders but on high dimensional expanders, then you gain some more properties. You can use the local pieces of this code to do local decoding, and then you get global list decoding, the algorithm. So that was a kind of a confidence building, because we managed to prove something non-trivial using these objects, and it gave us some confidence to the future. But let me also mention that this work, it was very nice, but really later it was improved and generalized to give algorithms for decoding much better codes, actually the almost optimal parameter codes of Tashma, and also for solving CSPs on high-dimensional expanders. So there was a lot of interesting follow-up work here. But one consequence also was that it built our confidence, and we decided to apply to the Simons Institute for a summer cluster. So it's like a short program, much more flexible. You don't have to apply too much in advance. So this was really perfect. And we applied for a summer cluster on high-dimensional expanders and codes, trying to bring together people. And this was really important because this community is still in the making, right? It involves both mathematicians, topologists, combinatorialists, group theorists, many different kinds of people, and of course, computer scientists. And we came to Berkeley in the summer of 2019, and we really had a great time. I think I came out of there with more open questions than answers, but I learned a lot. There was a lot of insight and a lot of understanding, like where we should look and what we should do. And there were several papers that came out of that summer cluster. Okay, so my last topic that I want to talk is about the C cube problem. This was really on our minds when we wrote the proposal for the summer cluster, and it's the following question. So if you have an error correcting code and you have a received word, it might be, I mean, it's a good question to ask, can I tell how much noise happened to this word? I mean, maybe it's not a code word, and maybe some bits got flipped. Can I quickly check how much noise has occurred? Okay, this can be very useful because cleaning a word from noise might take some computational effort. And so if I make a fast check and I see that there's a lot of errors, I can just ask, say, for a retransmission. So this is exactly the kind of property that locally testable codes give you. They allow you to do very, very fast, constant number of bits you need to read to check if a code word has undergone severe noise. And the idea of locally testable codes is not something that, say, Shannon or Hamming would have even thought about, because the kind of codes they were looking at, like random codes, they're just never going to be locally testable. So the source of this kind of object comes from the literature of PCPs. And it really hinges on the relationship between global properties, like being in the code, and small local views. So it was very natural for us to hope that high-dimensional expanders will enable us to construct LTCs. And indeed, we managed to finally do it. It took maybe a bit longer than we thought, but we managed to construct these LTCs. And this is the C cubed, refers to having both constant rate and constant relative distance, and also being testable with a constant number of bits. So this is called constant locality. We were even honored to be invited to give a talk at the Breakthroughs lecture series at Simons, and we got to get a beautiful graphic that Barry Bodeker, the graphic designer of the Simons Institute, did for us. We constructed an object that is like a high-dimensional expander, except the two-dimensional faces are squares and not triangles for some reason. And if you compare it to the graphic that he made for us in the summer cluster in 2019, to me, they seem very similar. Here on the right, you see that there's like underneath the water, what happened? Underneath the water, there's this high-dimensional expander, and on it you put the bits of the code, and then on top there are these checks. And on the left, you see that instead of triangles in the high-dimensional expander, you have squares, but the bits are still put on the squares. So it turned out to be quite similar. And I mean, in my career, it's quite unusual that you actually conjecture that you will be able to do something and then that it actually happens. So I feel very lucky to have had that. And thanks to the Simons Institute for participating in so many steps along the way of this road. Okay, let me finish with talking about what's next. Okay, so I feel that high-dimensional expanders, of course, they're so much less developed than expander graphs, but they have begun to deliver on their promise. They seem to be very interesting objects with some really interesting properties, and I hope that they will find more and more applications in the future. Of course, to me, it's very natural to hope to harness them to construct PCPs. In the past, locally testable codes actually came from PCPs, and it's natural to hope that if we manage to construct LTCs, we might be able to even use high-dimensional expanders to get new constructions of PCP, maybe cleaner, maybe better parameters, who knows. And indeed, we already have some future program next summer that might touch upon some of these topics, at least so I hope. Okay, so to end, I just want to say really thank you to the Simons Institute, thank you to Shafi and to the staff, thank you also to Jim Simons for supporting this institute. I feel that it's really been a tremendous success, and I hope to see you in the 20th anniversary.
Questions for Irit?
Hi, Irit. Thank you very much for your exciting talk. I really enjoyed it. Maybe it's a stupid question because it's not really my field, but I'll ask it anyway. I saw that in one of your slides, you gave a talk about this topic, and the title there was pseudo-randomness. And yesterday we heard a talk about obfuscation, and we've seen that the missing part is a low-degree pseudo-random generator. So my question is if you think there's any way in which locally testable codes or high-dimensional expanders can be used to construct low-degree low-degree PRGs.
Okay, thanks to the question. I actually don't recognize the voice. Who was asking?
Dor Bitan, I'm a postdoc here at Berkeley. I did my PhD at Ben Gurion.
Okay, cool. Okay, nice to meet you. So yeah, I mean, that's a wonderful direction to try and study. I believe in some sense, high-dimensional expanders are even better. They're not pseudo-random because the term pseudo-random suggests that you are trying to imitate properties that random object has, whereas high-dimensional expanders, we don't know of any random distribution that has these properties. So it's a better than random object, which is kind of crazy, but nevertheless, it's true. And really the way I view them, they're not pseudo-random, they're pseudo-dense. They're objects that are sparse, but locally they're very dense. Now, whether or not this can be useful to construct pseudo-random objects, why not? I mean, expanders are so useful, but I have no idea how.
Any other questions?
Hi, is there also a sort of a zigzag way of constructing high-dimensional expanders?
Oh,
Putting
wonderful question.
summitized pieces.
Sorry?
Or should I repeat the question?
No, I understood the question. So the question was, is there a zigzag way to construct high-dimensional expanders? So there are many attempts and several really beautiful combinatorial constructions of high-dimensional graphs that have certain expansion properties, but none of them have the really good high-dimensional expander properties. And when I say the really good, as a benchmark, I use this notion of local to global. For me, like a high-dimensional expander, really a high-dimensional expander, if when you look at the local pieces and you know something about their expansion, you can deduce global expansion. Then it has like the local to global feature. And the combinatorial constructions that are like zigzag that we have so far, they reach there almost, but they don't cross this barrier. So that's a great open question.
Thank you, Irit, for the wonderful talk to start off the day. Thanks.